Welcome to Algebra 2, Lesson 5.8. We're going to analyze graphs of polynomial functions. We have just 3 examples on this lesson, so we're going to try to just do one video. Our objective is for you to be able to use intercepts to graph polynomial functions. Alright, zeros, factors, solutions, and intercepts. Let f of x be in standard form and be a polynomial function. If k is a real number, then the following statements are equivalent. So we're talking about real values of k. 0. K is a 0 of the polynomial function f. Factor. X minus k is a factor of the polynomial f of x. Solution. K is a solution of the polynomial equation f of x equals 0. Now, to be honest, for those 3, we really wouldn't have to limit ourselves to k being a real number. This last one, we have to be talking about real numbers. X-intercepts. K is an x-intercept of the graph of the polynomial function. The graph of f contains k0. That's why we have to make this limited to real values of k, because imaginary values of k are not going to show up on the Cartesian plane, on a real number plane. Alright, we're going to graph f of x equals 1/6 times x plus 3 times x minus 2 squared. The first step for this is plot the intercepts. Because negative 3 and 2 are zeros of f, plot negative 3, 0 and 2, 0. Step 2. We're going to plot points between and beyond the x-intercepts. First, we're going to look and we're going to try to get some values, in between and among the zeros so that we can know what's happening kind of in the middle of the graph. So let's see. We want something between negative 3 and positive 2. So let's look at negative 2, 1, 0, and 1. And then maybe something a little beyond 2. So let's try 3. When you plug in negative 2 into this original function, you're going to get 1/6 times negative 2 plus 3 times negative 2 minus 2, the quantity squared. And when you simplify that, you get 8/3. We plug in negative 1 in for x, and we get 3. You plug in 0 for x, you're going to get 2. You plug in 1 for x, and you get 2/3. And you plug in 3 for x, and you're going to get 1. So remember, you pick x values, you generate y values using your function. Step 3 is to determine the end behavior. What happens as we go far to the left and what happens as we go far to the right? Because remember, this is just a polynomial function, so everything we've learned about in behavior so far still applies. Because f has 3 factors of the form x minus k and a constant factor of 1/6, it is a cubic function with a positive leading coefficient. So it has an odd degree and a positive leading coefficient, so that means it goes up to the right. Okay, it goes up to the right, down to the left. So f of x goes to negative infinity, goes far down as x goes to negative infinity. So here's our left end. And f of x goes to positive infinity. It goes up as x goes to positive infinity. So x going to positive infinity is far to the right, so the function goes up as we go far to the right. Alright, so you're going to draw the graph so that it passes through the plotted points and has the appropriate end behavior. So we found our x-intercepts, and we plotted them. And then all those little values from our table, we go ahead and plot those, and then we just apply the end behavior. So we go down to the left, and we go up to the right. And we've got a nice little picture of our graph. Turning points of polynomial functions. See right here, we go up, 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 and we turn and go down, 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 and then we turn and we go up, 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 up. These points are turning points. Okay? The graph of every polynomial function of degree n has at most n minus 1 turning points. Moreover, if a polynomial function has n distinct real zeros, no double zeros, no triple zeros, then the graph has exactly n minus 1 turning points. Alright, we're going to graph the function. Identify the x-intercepts and the points where the local maximums and local minimums occur. Alright. So we've got f of x equals x cubed minus 3x squared plus 6. And we've got g of x equals 5x to the 4th minus 6x cubed plus 3x squared plus 10x minus 3. So let's look at x cubed minus 3x squared plus 6. We're going to use the graphing calculator on this one to graph the function. That's always an alternative to actually making the little table. This one wasn't in intercept form. We can't complete the square because it's not a quadratic, so that doesn't help us. So we're going to need to use the graphing calculator to help us out on this. So we use the graphing calculator and we look at it. We can see that there's 1, 2 turning points. A turning point that looks like a maximum is a local maximum, and a turning point that looks like the minimum is called a local minimum. This maximum here is not the maximum value for the entire function because it continues on up to positive infinity. But locally, just around it, it is a maximum. Likewise over here, this value, this y value is not the minimum. It looks somewhere around 1. It's not the minimum because this end goes to negative infinity. So it would just be a local minimum. All right, so this graph has one x-intercept right here. See where it crosses the x-axis, and 2 turning points. You can use the graphing calculator's 0, maximum, and minimum features to approximate the coordinates of the point. So you can do, you can go in and have the calculator find the 0, and that'll give you the x-intercept. You can have it do the maximum, just like we did with quadratics, and then you can have it do the minimum right here, just like we did with quadratics. So the x-intercept of the graph, the 0, is negative 1.200. The function has a local maximum at 0, 6, and a local minimum at 2, 2. Oh, they must be counting by 2s here. Earlier I was thinking that was 1, but they must be counting by 2s. Let's look at g of x equals 5x to the 4th minus 6x cubed plus 3x squared plus 10x minus 3. So we're going to use the graphing calculator to graph the function. Notice that the graph of g has 4 x-intercepts, 4 zeros, and 3 turning points. Again, you can just use the calculator to go point by point by point by point to get the zeros. You have to decide whether you have a maximum or minimum whenever you're finding it. So here's an example of a minimum, here's an example of a maximum, and here's an example of a minimum. Now, this little guy here is strictly a local minimum because this point over here, the y value is even lower. This little guy right here is going to be just a local maximum because the function continues to go up to positive infinity elsewhere. Now, this little guy over here, the y value that goes with this point, that is going to be a local minimum, but it's actually the minimum of the whole function because there's no place where this function is going toward negative infinity. Both ends are going up. So this is an absolute minimum as well as being a local minimum. Okay. The x-intercepts of the graph are negative 1.140, 0.290, 1.820, and 5.030. The function has a local maximum at 1.11, 5.11. Now I do want to point out the maximum itself is the y value, but the book asks you for both points, or both coordinates of the points, just because you're going to be sketching the graph a lot, and on your rounds you'll see this. You're going to be drawing in the graphs too, and so you really need both coordinates to be able to plot your local maximum. But remember, the maximum, the term maximum there is referring to function value, so it's your y value. It has local minimums over here at negative 0.57, negative 6.51, and then over here, this is a local, but it's also the absolute minimum at 3.96, negative 43.04. All right, you are making a rectangular box out of a 16-inch by 20-inch piece of cardboard. The box will be formed by making the cuts shown in the diagram and folding up the sides. You want the box to have the greatest volume possible. So how long should you make the cuts? What is the maximum volume? And what will the dimensions of the finished box be? So here's the picture. So you're going to take a flat piece of cardboard, it's 16 by 20, and you are going to cut in X inches, okay? And that's going to be, it's going to form little x by x squares. This is a classic Algebra 2 problem. All over the country, who knows, maybe all over the world, Algebra 2 students are learning how to do a problem like this. We want the maximum volume here, so we want to know how big to make these cuts. Now let's talk about some restrictions. We can't cut or fold further than the whole 16 inches. So if we made it 8 by 8 square, we would be folding this thing in half. Okay, you would take all 16 inches and divide it in half. So that would be an upper bound. You can't do a negative cut. Okay, we can't go negative inches. So really, we're looking at x being somewhere between 0 and 8. That's just kind of a good thing to kind of keep in mind. So if you end up with a negative solution, you can reject it. If you end up with x equals, 13, you can reject it because there's just not enough inches in the width. Write a verbal model for the volume, then write a function. So the volume is going to equal the length times the width times the height. We know that. So the cut length is going to be 20 minus 2x because you're taking x off each end. Okay, so even though the whole piece of cardboard was 20 inches, once you fold it, it's going to be 20 minus 2x, x on either end. Similarly, the width is going to be 16 minus 2x because you start off with 16, but then you take off x from both ends to make it be able to stand up tall. So this is 16 minus 2x. And then what would the height be? That's right, it's x. Okay? So we're going to multiply the binomials together, and you just FOIL there. You get big numbers, but you get that from FOILing. So, because you get 20 times 16 is 320, and then you're going to have 20 times negative 2 is negative 40x, negative 2 times 16 is negative 32x, so those combine to give you negative 72x. Negative 2x times negative 2x is positive 4x squared. And then we've got this x over here that we need to distribute and write in standard form. So we'll have 4x cubed minus 72x squared plus 320x. All right, to find the maximum volume, graph the volume of the function on a graphing calculator. Consider only the interval 0 less than x less than 8 because this describes the physical restrictions on the size of the flaps. Remember, you can't make a flap bigger than 8 inches because there's only 16 inches across in the width direction. Okay, so when we consider just from 0 to 8, we want to maximize the volume. The volume is the y value, so we're going to find the maximum. Okay, so for the graph, you can see that the maximum volume is about 420, and it occurs when x is equal to 2.94. So the maximum itself is the volume, okay? And we want to know what x value it occurs at so that we know how big to make our flaps. So you should make the cuts about 3 inches long, 2.94. The maximum volume is about 420 cubic inches. The dimensions of the box with this volume will be about x equals 3 inches by x equals 10 inches by x equals 14 inches. And you get this value by doing 16 minus 2x. So 16 minus 6 is 10 inches, and you get this value by doing 20 minus 2x. So 20 minus 6 is 14. So that's how big the box should be. Okay, guys, that's it for today. Go ahead and do the problems to try on your own and come ready to do your rounds. And I will see you in class. Have a good day.